both of these cookies. Well, the question you ask then is, why don't I see 2 of those blocks for the top one? Because it is, it's a 16-byte username. They're 8-byte blocks. I should see 2 of those. Similarly, for the one that has 32 Cs, I should see 4 of those. So you think about that for a little bit, and what you eventually realize is that there's some padding. Maybe the username doesn't start right on a block boundary. It starts somewhere in the middle of a block. So you don't have 4 exact blocks of all Cs. You have one that has some Cs at the end of it, and then you have one that has some Cs at the beginning of it. So we have to figure out what the padding is and actually where the username is stored in the cookie. What's the byte offset in order to start attacking it? So we want to figure out where that is. So you start creating some more user accounts, and you can just create, you can be a little bit clever about what usernames you select in order to figure out where those offsets are. So in gray, above each one of these blocks, I list the username that we chose, and on the bottom is the token that we got back. So you can see that when I start with 5 Cs versus when I start with 6 Cs, I have a different beginning block. And when I have all Cs, I still have that. I have that the same as when I had 6. That's a little obtuse to understand just looking at it, but when you actually spread it out and kind of theorize where the username starts, I think it makes a little bit more sense. So the layout would have to be structured in this way for us to see that block in red be the same for our all C username and our username that starts with 6 Cs. And the reason that one in the middle is different is because it's got that D in it, so that changes the ciphertext. So now we know that we're using a block cipher. They're probably using ECB. The username is reflected in the token. And we know exactly where in the token that username lives in encrypted form. It's 2 characters of something followed by the username, followed by some other stuff that we have no idea what it is. But we know where the username is, and that's the important part. Okay, so now you want to become another user. So this is where now that you've done this sort of observation, this is where the attack gets formulated. So in this particular pen test, we knew via a different vulnerability that there was a user in the app called site admin. We got a list of all the different users, and this one sounded interesting. It doesn't matter if you knew this or not. Just demonstrating that you could impersonate another user is good enough. But in this one, we knew of another good account that would probably be interesting. So we knew there was one called site admin. So in order to impersonate that user, we need to have a cookie, an encrypted cookie that corresponds to that user. And that cookie would take the format that's shown here. It's 2 characters of we don't know what, followed by site admin, followed by more of stuff that we don't know. All we care about is replacing the username. So we register more user accounts. It's nice that it lets you set up as many accounts as you want. So you register one account that just starts with site ad so that you can get that first block. And then you register another account that has the MIN part of site admin at the right location in the username. So just a bunch of 1s for padding, and then the MIN. And now you've got some ciphertext out of that you can use. So you take those 2, you kind of put the pieces together, and you create a new cookie using those 2 pieces of data. And now suddenly you can provide this to the application. It's just going to go through and decrypt it. It's going to decrypt properly. The correct characters are going to be in the right place. It's going to parse the username as site admin, and it's going to allow you access to that application as if you were that user. So a pretty standard impersonation attack. So the recap from this is that you notice that we were able to subvert the entire authentication mechanism of this application without knowing anything about the crypto that they actually use. I still don't know to this day what algorithm it was. I have no idea what the key was. I have no idea what the key size was. I didn't have to brute force anything. We just looked at patterns, and we looked for some weaknesses in the way that they had implemented it. and then took advantage of those. I mean, the root cause of the vulnerability is that they used ECB mode as opposed to CBC. If they had been using CBC, we wouldn't be having this conversation. So it's not like it's a complicated root cause. There was no verification mechanism, so there was no sort of like integrity check at the end of the cookie, so that if I change part of it, that the integrity check doesn't match. If they had had an integrity check mechanism, that would have stopped the attack as well. Poor design was an issue because, like I mentioned at the beginning, they should be using sessions for maintaining authentication state. You should authenticate with your user and password once, and then you get a session, and you keep passing that session back and forth, rather than passing your username in encrypted form every time. So that's kind of a poor design issue. But ultimately, ECB should not be used because it lets us do this sort of ad hoc inline substitution and like mix and match the ciphertext together to come up with what we want. So that was a block cipher. Now let's look at a stream cipher. So this context was public-facing multi-tenant web application for a major financial services company. You could do a lot of stuff in here, including managing your accounts. I don't think it was a brokerage thing, but you could conduct some transactions. You could see your old statements and just information about your account. And this thing was using encryption all over the place. Every parameter that was passed, every link that you clicked on had these humongous parameters in it that were all, potentially ciphertext. So they looked like what we're seeing here. So in our URLs, in our links, we saw these long things. So like statement and view statement page. I'd see these long, identifiers for statement. And there were other things, file, context. There were a bunch of different parameters that all kind of used the same, or what we assumed was the same mechanism. The URLs changed every time you logged into the application. Even if you're the same user, you log in once, you get the links were like that, and then you log in again, and the links would be totally different. So it changed per logon and across different users. So they were never the same across users. So they were doing something very aggressive with their encryption. So we picked just one part of the application to take a look at, and it was the part that was dealing with viewing statements. So you could view your old bank statements or brokerage statements. And we knew what the statement numbers were because that was displayed to the user in the browser. You would say, like, show me statement 704 or whatever. And then the link to that, when you clicked on it, the URL was actually contained the long token there. So we gathered a bunch of these together and took the known. So this is a known plain text, right? We know what's probably being encrypted. It's probably the statement number, and then we know what the ciphertext is because it was present in the URL that you clicked on. So we started to look for some correlations between the statement number and the ciphertext. And again, this is after the base 64 decode, which is probably obvious. This is just the hex representation of those same tokens. So we noticed that when it started with, certain characters, 704432, you saw that same structure reflected in the statement token. So that's indicated there by the colorization. And then similarly, you could look at, okay, when I have a 2 as the second to last character, a 68 shows up at a certain spot.